Okay, so this is a review of energy, forms of energy, and conservation of energy for AP Physics. So I just want to remind you that the word energy in physics means an ability to do work or to cause a change. So something that has energy can do some work for us, or it can cause some type of change in its surroundings, or in itself or in its surroundings. So you can have several different forms of energy. Some of them are much easier to recognize than others, but energy comes in a couple of different forms that, one more recognizable than the other. The first form is kinetic energy, and this is the energy of motion. And it's really easy to tell whether or not something has kinetic, because if it's in motion, it has kinetic energy. And if it's not in motion, then it doesn't have kinetic. So that's pretty easy to recognize. The other type is potential energy, and potential can be a little bit trickier because it doesn't always depend on whether it's in motion or not, but it depends more on the condition or the situation that the object is in. So sometimes potential can be a little bit trickier to recognize. It depends on the position or the condition. So you have to look at something and say, is it in the right position or is it in the right condition to have potential energy, before you can just say whether or not it has potential. When we come to calculating these energies, again, kinetic is a little bit simpler. It's calculated with a K for kinetic energy. It's equal to 1/2 the mass of an object times its speed squared. This is not velocity, it's not a vector, it's just you take the speed, you square it, multiply times the mass, 1/2, you get your kinetic energy. The unit is going to be the same unit for all energy, which is a unit called a joule, which we symbolize with the letter J. So all energies are going to be in this unit of a joule. Potential energy comes in lots of different forms. So there's chemical potential energy, which we won't discuss in physics, but that's like the energy that's formed in the breaking of bonds, like when you eat a piece of fruit or an apple or whatever, and your body breaks those bonds apart and takes the energy that's stored in those bonds, then that is called chemical potential energy. That's not something we'll discuss, but the two that we will use in this class are gravitational potential energy, which is energy due to the gravitational pull on an object, and the other one is elastic potential energy. And elastic potential is the energy due to the elastic nature of an object. So when it comes to gravitational potential energy, it's due to an object being a certain height off the ground, and gravity pulling on it. Okay? And so the object being a certain height off the ground has the ability to cause some sort of change, because if you were to drop it, it would fall down, and it would speed up as it fell down. So that would be the type of change that it would have. And it could do some work for us also. So there's a lot of different things we could do with this gravitational potential energy. Like if we attach the object to a pulley system, we could cause it, if we pull down on it, it could cause something else to lift up. It could do work for us in any different number of ways. So gravitational potential energy is due to the height above the ground, how high am I above my 0 point, and to the amount of gravity, because there's going to be more gravity on Earth, less on something like Mars or the Moon, so you'd have less gravitational potential energy on a place where the gravity is less. The formula we use for gravitational potential energy is U. U is actually the symbol we're going to use for all potential energies, and it's going to be U with a G, so it's gravitational potential energy. It's equal to M, the mass of the object, times gravity, whatever the gravitational pull is. On Earth it's 9.8, and then times the height above the 0 point. Okay, so M is the mass is going to be in kilograms. G is going to be your gravity, and on Earth that's 9.8 meters per second squared, and H is going to be your height, and that's in meters. When you put all of those units together, you get a kilogram meters squared per second squared, and that is this unit called a joule. You get actually the same unit over here. If you work this one out, you get kilogram meter squared per second squared, and that's a unit called a joule. Okay, kilogram, pardon me. So that is gravitational potential energy. Elastic potential energy is due to the elastic nature of an object. And not everything has an elastic nature, so not every object is going to be able to have elastic potential energy. But objects like springs and bungee cords and those sorts of things will be able to have, they have this elastic, stretchy nature to them. They tend to want to return back to their unstretched state, that sort of thing. Those objects could possibly have elastic potential energy. The way that you would give them elastic potential energy is you would stretch them out of what we call the equilibrium. So if you had a spring that was just sitting there minding its own business, and it wasn't stretched or it wasn't compressed, we would say it's in equilibrium. In this state, it does not have any energy, any elastic potential energy. But if you take that and you stretch it out of that equilibrium so that now the spring is in some stretched state, now it wants to go somewhere, so that if you release this object, it's going to go flying back. So anytime you stretch it out of its equilibrium position, then you're going to give that object an elastic potential energy. Okay? The amount that you stretch it out of equilibrium, like from its equilibrium position out to this place where you stretch it, we call that its stretch or its compression, and we give it the symbol X. X is going to be in meters, so the amount that you stretch it. And it will make a difference. The more you stretch something, the more potential energy you give it, or the more you compress it. You can do the same thing with the compressing. You can take the spring and you can push it in tighter. And then when you release it, the object's going to want to spring back the opposite way. So you can compress it in a certain amount. So you compress it or you stretch it out of equilibrium. So the X is the distance out away from the equilibrium. And the amount that you stretch or compress it will control how much elastic potential energy it has. The other thing that controls the elastic potential energy is something called the spring constant. And the spring constant is a number. It's the letter K is what we use for spring constant, lowercase k. And it's a number that's assigned to every spring or anything that's elastic that tells you how much that spring stretches when you put a force on it. So how much it stretches when force is placed on it. So if you think about certain, let me just write this before I forget what I'm saying. Okay, when you think about certain springs, some springs are much easier to stretch, and it doesn't take much, and you just put a little bit of force on them and they stretch really easily. And then some springs, the ones that are much stiffer, they take a lot more force. So to get them to stretch the same amount, you have to place a lot more force on those. So those springs that are stiffer, we say, have a higher K value because they take a lot more force to make them stretch out of their equilibrium. So these two variables, the amount you stretch it and the spring constant, are what control the elastic potential energy. So the formula we use for elastic potential energy is 1/2, we'll put a little e right here, times the spring constant times the amount stretched squared. Okay, now the unit. The units that we have here are the X is in meters, so we have meters squared, and the K is actually in a unit called a Newton per meter because it's a force per distance. Since we defined it as how much it stretches when a force is placed on it, you can basically think of this as how much force did I have to place on it to get it to stretch a certain distance. So that's where Newton per meter comes from. When you put these two together, you end up getting the meters, 1 meter cancels, and you get a Newton meter. Well, a Newton meter is actually just, back up here, a joule. A Newton meter is a joule. Okay, it's a kilogram meter per second squared times a meter, so that makes it a joule. All right? So that is elastic. So we have our 3 types of energy, and the last little bit of this puzzle is conservation of energy. And that is what happens when the energy in a system is changing forms. So it's going between elastic and potential, potential and kinetic, kind of back and forth. So when that happens, we have to obey the law of conservation of energy, which says that the total energy of the system is not going to change. It should be total. So the total energy remains constant. So the energy can change forms. It can go from kinetic to potential and back and forth, but it's not going to change as long as you do not have any dissipating forces. So dissipating forces are forces that tend to take energy out of the system and turn them into forms that we can't get back. So one example of a dissipating force is friction, because friction, when you have friction, it takes energy out of the system and typically turns it into heat. So if you think about, like if you rub your two hands together and they get warm, it's because that friction is turning into heat. You can't take the heat that the friction, that energy gets turned into heat, you can't take that heat and put it back into the system. So we call it a dissipating force because it actually will remove energy from the system and turn it into a form that we can't get it back, or in what we call a non-useful form. So heat is, in this case, oftentimes a non-useful form because it's a side effect. So you can think, I mean, you have this issue all the time, like a car engine has issues with friction, and that's why the engine heats up. And we have to try to keep the engine cool because all that heat, you can't get that heat, you can't take that heat and actually use it for anything useful. It's just dissipated into the environment. Okay? But as long as we can ignore friction, then we can say the total energy of the system is going to remain constant. So if you think, for example, I'll give you two examples and then we'll be done. One example is a roller coaster. So if you have something on a roller coaster, at the very peak it has the maximum potential energy, gravitational potential energy that it's going to have. No elastic, right? So it's got its maximum because it's its highest up. Down at the bottom where it's moving fastest, that's where it's going to have its maximum kinetic energy, down at the very bottom, because it's got its fastest motion. So you have a transformation that goes on where potential turns into kinetic. And then as you go back up the next hill, the kinetic is going to turn back into potential as it gains potential and loses kinetic. It slows down and gets higher up. So you have a constant changing of energy going on. So when you're at this point, it's still moving, so it has potential and kinetic, but when you add those two together, they have to sum up the maximum it had before. Okay, so you have to always look at what your maximum amount of energy that you had was, and it always has to add up any given time. And so you can have transformations going on all the time, but the total needs to add up to the total amount that you have. Another example is a toy dart gun. So with a toy dart gun, you have a spring-loaded gun that is minding its own business inside here, and then you take it and you compress it a certain amount. And when you compress it, then you give it some sort of elastic energy. And then when you release it, the dart or whatever it is, the bullet, comes flying out of the gun, and at this point it has kinetic, but the spring is not compressed anymore. So you have the elastic of the compressed spring turning into kinetic of the projectile. And so you have a transformation that happens where the spring's elastic turned into kinetic for the projectile. So you would say 1/2 kx squared, where this x would be the amount it got compressed, equals 1/2 mv squared, where the v would be the amount of speed the massive object has leaving the gun. Okay, so that's another example. The problem that you have for homework deals with another type of elastic toy, but the elastic toy is actually jumping up, so it's a little bit different, but it's still using conservation of energy and transformations.